So now that we've discussed user and group management, let's explore file system permissions. So we'll label this section file types, permissions, as well as symlinks, symbolic links. Now in Linux, file permissions are represented by 10 bits. And the features include the ability to restrict / control access to files, which also includes directories. So note, 10 bits represent permissions for files, which also includes directories. And to examine those permissions, we use the ls command. Use ls with the long option to examine permissions or GUI application like Nautilus, which is similar to Windows Explorer, and then you can navigate to the properties of a file or alter the output such that the permissions are displayed within the window that you are looking at. So we use ls-l wherever we are to see those 10 bits. And let's take a brief look and extract something from Linux CBT's home directory. We don't need to be root, so let's just drop out of the root shell and execute lsl. So here is the test RH5 subdirectory, and we can work with an item that we recently created, the regex test.pl file. Let's copy this entry and discuss the 10 bits that constitute permissions. The first bit in this particular case, since it's a file, is a hyphen or is unmarked, indicating that the item is a file. So bit 1, or first bit, equals file type, where a hyphen means file and D is equal to directory. But there are other types of files, such as named pipes, devices, and others. But for our intents and purposes, files and directories are simple, and we come across them more so than other types of file objects. The second bit, in fact, second, 3, and 4 control permissions that are associated with the owner of the object. So second through 4th bits equal owner's permissions. And those permissions can be organized in any of the following: read, write, and execute. Now each of these permissions bits, read, write, execute, which we see for the file object regex test.pl, also has an octal representation. R is equal to read, but it's also equal to 4. W is equal to write, but it is equal to also 2 in octal notation. And last but not least, to complete the octal representation, which must add up to 8, thus the name octal, execute represents, or is represented by 1. When we add them all up, 4 plus 2, 6 plus 1, 7, we get the full bit representation, or total sets of permissions that can be assigned to the item. Now you may be wondering, doesn't add up to 7? Well, if the item isn't flagged, it occupies position 0, so 0 through 7 represents the octal set. As you see with the case of a file where there's a hyphen, this particular item, or this bit, is currently on set, occupying the 0th octal value. So read, write, and execute are the permissions that are permissible within a Linux file system, regardless of file system type. So it can be riser, ext2, ext3, jfs, xfs, you name it. These are the types of permissions you may set. Read, write, and execute, and they have the values 4, 2, and 1. Bits 2, 3, and 4, or 2nd through 4th, correspond to the owner's permission. Now when you use long format to return the permission information, we see the owner of the object immediately following the number of symlinks. So this user, Linux CBT, owns the object. Bits 5, 6, and 7 represent the group owner's permission. So 5th through 7th bits equals group owner's permissions. And here again we have the same permission sets, read, write, and execute. So it follows through nicely. And we wrap up with the last sets of bits, 8, 9, and 10, which represent everyone else. So 8th through 10th bits equals everyone. In other words, the world, anyone who has access to the file system, whether via Samba, NFS, or locally connected using SSH, Telnet, etc. The 8th through 10th bits also can be read, write, execute, but they also may be hyphen, and we should just include that hyphen equals none, which is equal to 0. So for each of the groups you may see hyphen, which indicates none or 0, with the exception of the first bit, which represents a file if there's a hyphen. Now there are tools that allow you to influence or change the bits associated with a file. For example, looking at this regex test.pl file again, we changed the permissions to make the file executable because we created it as a Perl script. We can remove the permissions, the execute permissions, for example, using the change mod command. So task, manipulate file permissions using change mod. Change mod changes the mode of permissions on files. Now to remove the execute permissions, we can do the following. Change mod. Now before we added using simply plus execute, we can minus execute, followed by the name of the file regex test.pl. And if all goes well, when we relist the contents of the directory, the file will no longer be executable. That's lsl regex test.pl, and there you see the execute bit, or the bit which occupies the last placeholder, which is also equivalent to 1 for each of the groups of owners. The owner, group owner, and everyone else has been unset. So now the permissions have been changed to simply read, write, read. These permissions can be converted to octal notation and reference, especially when communicating between administrators. So now when we look at the file, it has the octal representation of 664. For the owner, read plus write equals 2, or equals 4 plus 2, which equals 6. So read write equals 6, or 4 plus 2. And that applies, of course, to the owner of the object. Ditto for the group owner. However, we have simply read, which is equivalent to 4 for everyone else, or the world. And that's how we come up with octal notation of 664 for this file. Now this 664 can be passed to change mod to influence the permissions of the file. For example, change mod 664 regex test.pl achieves the same thing as removing the execute permission from the file. And conversely, if we wanted to turn on execution permissions, we could indicate change mod 774 to influence the permissions, or 775 so everyone can execute the file. So this enables execution for all users, and this removes execution for all users. Let's give it a try. Currently execution has been removed, so let's reapply it. We'll re-lsl regex test.pl, and now we see execute has been turned on for the owner, the group owner, in this case bits 2, 3, 4, 4, 5, and 6, And for everyone else, read execute. Write has been skipped. And whenever the write bit is not present for obvious reasons, the user who is within that context, such as everyone else, will not be able to write to the file. However, we're logged in as the group or the user owner, the owner of the object, so we will be able to write to the document. So now the file is flagged as executable by all users. Let's remove the executable permissions by setting 664. And then we'll use command chaining to lsl regex test.pl, where you see execute permissions have been removed. So this way, it can no longer be executed by default unless we reference Perl first, followed by the name of the script. So long as you memorize that R is equal to 4, read is equal to 2, and execute is equal to 1, you can combine the permissions as you see fit. So for example, let's suppose another task would be to make regex test.pl readable and writable by the owner and no one else. So next task would be to ensure that regex test.pl is readable or read-write by owner and no one else. To do so, we'd execute a change mod, and if you think about it, read plus write is equivalent to 4 plus 2, so we know we need 6, because the 6, or the first value, corresponds to the owner of the object. We want no other user, including the group owner, to have access to the file, so we simply turn off all bits by indicating 0, and ditto for everyone else. So 600 will make this file readable and writable only by the owner of the object, with one exception. And that exception is the root user of the system, or a root equivalent. So change mod 600 regex will do just that. And we should note, file will now be RW by owner, and that happens to be the user Linux CBT, and root, as you are unable to lock root out of a file. The interface, for example, may say you're unable to read it, but root can always change the permissions to the file. So let's execute the change mod, and then lsl regex test.pl, where you now see most of the bits have been wiped out, with only read-write, which applies to the owner of the object. We know because the read-write permissions are in positions 2 and 3, which correspond to the owner. 2, 3, and 4 correspond to the owner. 5, 6, and 7 corresponds to the group owner. 8, 9, and 10 corresponds to everyone else. So let's test this all out. Let's nano regex test.pl, and we'll insert a comment at the bottom. And we'll try to save the document to be sure that we can update it. Notice Nano had no problems updating the document. We can LSL, compare and contrast between the current timestamp, and it has worked as expected. Now how about if we attempt to modify this document as someone else, such as student 1, from a separate shell? We'll SSH as student 1 to the local host, which will prompt us for authentication. Now we're in as student 1, in student 1's home directory. Let's navigate to home Linux CBT test RH5. And it doesn't let us interact with the file. It doesn't even allow us to navigate into the directory. Let's take a look at the permissions one level up to see why that could be the case. So we'll lsld test RH5, and the directory is readable by everyone else, so let's go one level up to the Linux CBT directory, and that's why. The Linux CBT directory is not readable by the user, or other than the user owner as well as the root user. So with that said, we would need to move the file or change the permissions on the directory. So if we wanted this directory to be readable by all users of the system, let's navigate one level up and do so. We'll change mod 755 Linux CBT. Now we have relaxed the security, and student 1 should be able to take a look at it. Let's lsltr home Linux CBT test RH5, and now we can interact with it. So with that said, we will nano regex test.pl, which currently is set to 600, and you'll see permission denied. Error reading home the full path to regex test.pl, permission denied. Now how about as root? Let's log out of this session, and now we're in as Linux CBT, and then SU in, and try to interact with the document. So now we're in as root. We'll nano regex test.pl, and as you can see, we're able to read the document. Let's include a comment towards the bottom. End root. We'll save it. No problems whatsoever. When we cat the contents of regex test.pl, root was able to make changes, although on the surface the permissions don't seem to indicate that root will be able to make changes to the document. Root always has, or root equivalents, meaning other users of your system with the UID 0 and group ID 0 will be able to make changes to files that other users of your system have created, regardless of permissions associated. So you'll use ChangeMod to make those sorts of changes, to make files executable, non-executable, read-writable, so on and so forth. We could even lock ourselves out of making changes to the file, meaning the user Linux CBT, by making the permissions more restrictive. So let's list as a separate task. Ensure that regex test.pl, and we can do so as root, by the way, instead of the user who's currently logged in, Linux CBT, who owns the file, is read or readable by owner and no one else. Well, if a file is only readable by the owner, that means the owner can't write to the file. So instead of change modding to 600, which is read-write, we know that the read octal value is 4. So 400 regex test.pl followed by an LSL. Regex test.pl will do the trick. And again, we can affect this as the user root or as the owner of the file, Linux CBT. Let's change into test.rh5, LSLTR, then give it a try. Now we see that only the read permission is set to the file. With that said, let's modify it, or attempt to modify it using nano, and we'll create a new entry. We'll indicate end Linux CBT, then attempt to save the document using Control-X, Y, file name to write, regex test.pl, notice error writing the file. Now at this point we could optionally save the file as a different file name because we ultimately have control over the directory, but we cannot update regex test.pl. So let's try to save it as regex test2.pl, and that'll work. But we cannot make changes to regex test.pl, which is why the test2 version is 19 bytes larger. Let's go ahead and remove regex test2.pl as it's not necessary, and then change the permissions back to 600 on regex test.pl. But before doing so, let's just show you that even though the file currently has 400 permissions, the user root can still make changes. So we'll now, and let's just confirm that the directory is indeed set, and the file is set to 400, we mean. So we'll nano regex test.pl, navigate towards the end, and copy and paste end root twice. Save the changes. Notice, no trouble whatsoever. Root's never denied from being able to make changes to files on the system. Now, in addition to octal notation, as we've alluded to earlier, ChangeMod supports alpha or string values that represent the permissions that you can enable using octal notation. So note, ChangeMod supports string values which represent octal values. So for example, if you wanted to change the execute bit, you'd ChangeMod and either plus or minus X on the file name. If you wanted to change, let's say, the write bit, then just indicate W instead of X. Ditto for the read bit. So you can modify each of the bits using strings, string literals such as RWX. You can influence which user the permissions applies to. For example, by indicating U plus X to add the execute permission. Let's take a look at that to see how it would apply in the regex test.pl case. So we'll change mod u plus x regex test.pl followed by an LSL regex test.pl, and now you see the owner, after having executed u plus x, the owner's permission has been updated to read plus execute. So u plus x updates owner's execute permissions on the file. Similarly, let's go ahead and show you an alternate way to execute this o plus x. Let's show you what would happen when we do this. We're going to set the permission back to 400 and then execute o plus x. So change mod 400 regex test.pl. Now it's back to 400. In fact, we indicated 4000, incorrect permission there. Now it's back to 400. And now let's attempt to change mod, instead of u plus x, o plus x. And you'll see that this now applies the execute bit to everyone else, or to other, which is what the last 3 bits represents. So this changes, instead of the owner's, others' permissions or execute permissions on the file. And again, now if we indicate g plus x, this will update groups or group owners' execute permissions on the file. Before doing so, let's return the permissions to 400, and then instead of o plus x, we'll change it using g plus x. And you'll see that now the group users' permissions have been updated. Instead of bits 1, 2, and 3, we've got 4, 5, and 6, the 6-bit being updated. So when you want to influence using change mod, changes to the owner, use u, to everyone else, o, to the group owner, g. Or if you remember the octal notation, use that and it will work in place of the string notation. And this works for any permission, not just execute. For example, let's reset the permissions to 400, and then instead of simply g plus x, we could say g plus rwx. Now the group owner has read-write execute permissions to the object. If we wanted the true owner to have such permissions, change this to u plus rwx. Or what if we wanted everyone to have these sorts of permissions? Well, a plus rwx. So change mod a plus rwx is equal to change mod 777, which is a dangerous permission to apply, but sometimes is necessary in order to provide all users the ability to read, write, and execute the file. Try to avoid using 700, however, as again, it is too liberal, so we'll set it back to 400. So that's the job of change mod, to change the permissions. Now we did mention that you can, from the GUI environment, make these changes. You don't have to rely upon the shell-based environment. Simply navigate to Nautilus, navigate to the directory, in this case testRH5, pops up in a separate window, find the file. Here's regex test.pl. Because it's a Perl script, it's represented by the following icon. Navigate to properties, where you'll find the permissions for the object beneath or within the permissions tab, and you'll see that the permissions are broken out by groups of owners, including the owner, the group owner, and everyone else. Since it's set to 400, the owner's permissions are set to simply read only, as opposed to read and write. Group owners, Linux CBT, and it's set to none. Others is set to none, but you can change that. And an SE Linux context is set to file_t. And execute permissions aren't set, but if you want, you can allow it to be executed, which updates the permission set if you select it, if you change it. So you can change permissions. For example, let's go ahead and set this to read and write, and read and write for everyone, and allow execute permissions. Now we've made changes, and from the shell, let's just move this over so it's within view. When we re-execute our LSL of regex test.pl, notice it's now rwx, or 777, because we clicked on the execute permission. Navigate back to this, properties, and we'll change in the permissions tab from read and write. Well, we can drop execute, which will drop it instead of to 777 to 666. Let's take a brief look at that. Now it's 666, 4 plus 2, 4 plus 2, 4 plus 2 for the owner, the group owner, as well as everyone else, which still is too excessive. If we want 400, we'll set the owner to read, which is 4, everyone else to none, as well as the group user none. And then, in the background, you'll see the permissions have been updated. Now, by the way, as mentioned before when we use the stat command, whenever you change attributes of a file, stat will reveal or show you the updated attributes. If you compare it to the current timestamp, which is 1602, you'll see that the file was last accessed at 1602, but was also changed at 1602. So any permissions or attribute changes to a file are recorded in the file system and are accessible using the stat command. You can always use it, whether accessing it as a function through Perl or directly from the shell as simply the stat command. Now there are other commands that allow you to change ownership, group ownership. For example, chown and change group. Let's navigate back to our shell or back to our gedit window and just introduce chown. Permits changing of ownership of files. And by files we also mean directories. For example, chown root regex test.pl changes ownership to the user root for this particular object. Let's give this a try. Now, we're going to do this first as the user Linux CBT, just to show you what happens when you try to change ownership to a user that you currently are not. So let's do so as Linux CBT. Well, who am I? lsltr regex. It's set to 400. Now let's paste it. And notice, changing ownership not permitted, although we own the file. Let's take a look at it to see if it even changed it, and it hasn't. However, if you change ownership as the user root, it's a different story. No problems, no errors returned. Let's lsl regex test.pl. You need the wrong format, and now the file is owned by root, which means if the user Linux CBT tries to modify the file, it'll fail. Let's try to modify, or even read the file. It fails. Root is now able to read the file, and root was always able to read the file. So usually you change ownership as the user root. You can also use chown, and by the way, you don't need to memorize any of the options, to change group information by delimiting the user and the group with a colon. So for example, an LSL of all the items in this directory show that they're owned with the exception of regex test.pl by the user Linux CBT and the group Linux CBT. What if we wanted this file to be owned by Linux CBT but by the group sales for which the user Linux CBT belongs? Well, let's go ahead and show you how we do that. Chown Linux CBT colon sales regex test.pl changes owner and group to Linux CBT sales, which means if you are a member of sales and have access to the test.rh5 directory, you'll be able to interact with the file, providing there are permissions that are associated with the group owner. So let's just double check that to see whether or not that's the case. Currently, no, it's set to 400. Nonetheless, we can still update group information and user information. Let's LSL again it. Now you see it's owned by the original owner, Linux CBT, and by the sales group. But there are no permissions in bits 4, 5, and 6 for the group sales. So if you're logged in on the system as a different user, you won't have rights to the file. So that'll be our next task, using chmod. Update regex test.pl so that owner and group owners, or owner, may modify the file. To do so, we'll chmod. Instead of string literals, let's go ahead and indicate 6 for the owner, 6 for the group owner, and 0 for everyone else, regex test.pl. We'll navigate to the shell, follow that up with an LSL of regex test, and now we see the bits have been assigned for the owner, read write, and the group sales. So let's prove that this all works. As the user Linux CBT, let's nano regex test.pl, navigate towards the bottom, and include a comment end Linux CBT, just so that we have shown that we've written something and we've updated it. However, the next test will be to attempt to modify the file as, let's say, student1. So let's su in as student1, and then nano home Linux CBT test rh5 regex test.pl, navigate towards the bottom of the file, and then end with student1 via sales group membership. Save the changes, and the file's been updated. We can confirm it from a different shell by simply catting the contents of regex test.pl, and there you see student1's been able to make a change to the document, despite the fact that the document exists beneath Linux CBT's home directory. And that's because student1 belongs to sales, a group which has read-write access to regex test.pl. So that's how you'd implement basic group membership and permissions to be able to make changes to files within your environment. Now, there are other types of permissions, such as setuid and setgid. With setuid, you change the permissions on an object so it executes as the owner of the object. So setuid, again, features ability to execute file as owner. And there are many such setuid programs in the Linux environment, where when it's executed by a non-root user, it actually executes as root. And it is a dangerous feature, but it's required for functionality. To enable setuid execute, change mod will first and foremost ensure that the appropriate user owns the file. So in the case of, let's say, test.pl or test regex or regex test.pl, that is, it's owned by Linux CBT, and if you want this file to be executed as user Linux CBT, regardless of who executes the file, that's where setuid helps you. First, of course, we need to ensure that it's executable. So change mod for the owner plus x regex test.pl. Now when we lsl regex test.pl, we see that the owner can execute. But to setuid, we change mod and we use a special prefix of 4, followed by the appropriate bits, such as 7, and in the case of the group owner, it's 6 for read-write. So it'll be 760 regex test.pl. This will ensure that the Perl script always executes as the user Linux CBT. That's the purpose of setuid, to be able to execute a program as another user, in particular as the root user. When you execute change mods 4760, 4 being the special prefix for setuid, it will change the actual color of the regex test.pl as it's represented in the directory tree, and it also changes the execute bit for the owner from X to S, so that it looks like the following. And the S in the execute position means that the program will execute as that user. So whenever you run regex test.pl, it will run as Linux CBT. There are countless reasons why you may want to do this in a Linux environment. Have a program always run as a given user, in particular for permissions reasons. There's another feature, setgid. This is neat when you need to ensure that users apply certain permissions unbeknownst to them to a directory structure. So ability to enforce permissions to a directory structure. So if you want every single time users write to a given directory, consistent permissions are applied, then you'll want to use setgid. And we do so using change mod with the to prefix. And then you apply the permissions that are appropriate, such as 777 or 755 to the directory name. Now we're going to go ahead and make a directory, so we'll make directory root sales, and and then we'll change mod 2755 root sales. This will ensure that permissions are inherited from the top level of the directory structure. So let's go ahead, and we need to do so as root. We can't create the directory as student1. So make directory /sales. Now we have LSLD will tell us a /sales entry, but it's owned by root. We'll chown. Let's make it owned by linuxcbt.sales /sales followed by LSLD /sales to be sure that the permissions have been written. So now the object's owned by linuxcbt and sales. setGID helps us if, again, we want to ensure that all objects beneath sales are owned by the users you see here, linuxcbt and sales, owner as well as group owner. This is where we'd specify, for example, 2755 or perhaps 2775 to ensure that the sales group is able to write to the directory as well. And this is a great way to facilitate the sharing of documents on your system. So now, after this is applied, we'll LSLD again, /sales. We will see that the group bit has been set, the execution bit has been set to indicate that it's set GID, meaning any object that's written in this directory will have the sales group definitely assigned. That's very important because, again, if you want users to be able to share files on a Linux system, you need some commonality, some way to tie the users to the object. And the way to do it is either via the UID or the GID. Now let's show you how this works. We're going to create a file as linuxcbt. So create a file in the /sales directory as linuxcbt. Now generally in a Red Hat Enterprise environment, when you create a file, the permissions are written such that the user linuxcbt and the group linuxcbt owns the object. But in a setGID environment, the user will own the object, and the group that's assigned to the directory, the top-level directory, will also own the object, such that other users will be able to manipulate the file, consequently promoting sharing. So let's use sequence, and we'll go with sequence 1,000,000 into a file called linuxcbt.1,000,000.txt. We'll create this file as a user linuxcbt in /sales. Let's find a shell where we are linuxcbt, and here it is. We'll navigate to the root. We'll LSLD sales just to be sure that we can write there. And as you see, linuxcbt owns the object. Sales also owns the object. We'll navigate into sales. And then Control-Shift-V our item. And again, when you normally create files, we'll LSL to show you, the file is written with permissions such that the owner as well as the group owner linuxcbt in the Red Hat environment would own the object. But in this case, linuxcbt and sales owns the object that is. Also note the permissions, read write, so that other members of the sales group, such as student1, are able to modify the file. So from a student1 shell, let's SU in as student1, we navigate to sales, and we'll see the object, and for IDs, you'll see that we belong to sales as well as marketing. If we nano linuxcbt 1,000,000.txt, well, it takes forever to open it because it contains 1,000,000 items, and navigate all the way towards the bottom or the beginning or wherever. Since it contains too many items, let's go back to the top and just insert a value. And we'll just indicate a value 0, which didn't exist, and attempt to save the document. Notice it saves it. A less of the file shows that 0 is now there, we've inserted it, and an LSL shows that the permissions have been unchanged. The timestamp's updated, we've updated the file, but the permissions are intact. Now how about attempting to create an object in here as the user student1? Again, sequence 1,000,000 into student1.1,000,000.txt will do the trick. Notice no errors, no permissions errors thus far. That means we're writing the file with no trouble. Notice that the file is owned by student1, but also by the sales group. This is again the power of setGID, because now any member on your Linux system of the sales group, or any member throughout your environment if you're using LDAP or some sort of enterprise technology for sharing users like Active Directory, so long as they belong to sales, they'll be able to interact with the objects created in the sales directory. This is perfect for projects and for sharing. So Linux CBT can modify both the file created by Linux CBT and Student One, and vice versa. So that's the application of setGID versus setUID. With setUID, you generally want to execute a program as a given user, usually as the root user. Now let's show you an example of a setUID program that is set to setUID root. Well, which password? This is the program used to change your password. It's in user bin. Let's copy its path, and then LSL, it's not a file, it's not a directory, so we don't need D. And notice that it's returned in red. The shell has colorized it with a red highlight. But more importantly, look at the third bit, or the, in this case, fourth bit, which is the third usable permissions bit for the owner, and it's S versus X. This tells you that whomever executes password will do so as root. And that's the purpose of setUID as opposed to setGID. So when we execute password as the non-privileged user Student One, it prompts us to change our password, but it's really going to make changes to the system as the root user. Now in this case it throws an error because we are not permitted to change our password as per the settings in the etc shadow file, for which we have no access to. If we attempt to interact with it, it'll throw an error. So again, thus far we've covered quite a few things regarding file system permissions. We've covered the octal representation, the change mod utility, the string representation, read, write, execute, the number of bits, 10. We've mentioned two types that you're likely to see, hyphen meaning file, D for directory. Perhaps we should just show you a directory entry. And LSLD /sales, for example, will do just that. There you see in the first bit, it's D instead of hyphen. And in the dev tree, there are all sorts of items that are non-directory items, such as a character device, and many of the terminals that we use are character devices, as well as block devices. These are other types of devices like hard drives. So there are many types or file system types, or file types that you'll find in the first bit. We've described the other 9 bits. We've talked about change mod, chown. There's also change group, which we haven't mentioned. There's also setUID, the ability to execute a program like password, which the setup process has done for us already. There's also setGID, which allows us to share directories. This is a great way to share common space. And just a quick note about change group. Permits updating of group permissions. But you can use chown to do that. So which change group tells you it's in user bin, and for any object, for example, let's take, and we'll sort it by most recently created items, regex test.pl. If we wanted to change the group, we'd simply change group, and for any legitimate group in our group file, we can specify, such as marketing, regex test.pl followed by an LSL of regex test.pl. But again, you can use chown to do that, so you don't necessarily need change group, but it's there in the event that you need it. So these are the types of utilities that you'll use to change permissions. Whenever doing setGID, use a prefix of 2. Whenever doing setUID, use a prefix of 4. And there are other items regarding permissions, but these are the main ones, such as the sticky bit, which you'd reference using 3 as opposed to 2 or 4, which allows you, in the case of a directory, to ensure that a user cannot remove other users' items. And perhaps it's worth mentioning, sticky bit features, in the case of a directory, ability to ensure that users cannot delete other users or others' files in a directory. For example, the temp directory is a good example of the sticky bit implementation. LSLD of /temp will reveal the last bit being T. This is the most commonly referenced example of a sticky bit on Linux systems. What this basically means is that users cannot delete other users' files in /temp. So if you take a look at /temp, for example, lsltr/temp, you'll find multiple items. It's a general space for different people to write items. Notice the items for Linux CBT are readable and writable and executable only by the user Linux CBT, of course by user root. But this user cannot remove this user's files, and ditto for student 1. So it's a way to allow users to share a space but not run into each other. And that's a sticky bit. And you implement it using changed-mod and 3 as a prefix. So changed-mod, for example, 3777 on a directory such as sales ensures that /sales will not have clobbered or will not lose files from incorrect users. So that's why you'd implement the sticky bit, that is. Now we're going to be looking at quotas as well as symbolic links in the subsequent section. We'll begin by discussing symlinks, both soft and hard, and then show you how to implement quotas.